In this lesson, we're going to learn control valve basics so that when we encounter control valves in the process industries or designing systems where a control valve is necessary, we can be able to determine what the proper flow rates going through a control valve are, or if we've discovered some problems with an existing control valve, we can then determine what might be the problem. The goals of this lesson are straightforward. One is to be able to predict the flow rate of liquids and gases going through a control valve when we have been given the valve size and process conditions. Also, we're going to determine if choking, which I'll describe later, will occur in a valve, which will limit the flow rate going through the valve itself. Let's take a look at an overview of what a control valve does. The valve itself takes an upstream pressure of a fluid, which we call P1. It enters the valve and goes through a flow reducer and then exits out the control valve at a pressure P2. One thing that we need to be aware of is coming out of the fixture in the valve, we have what's called a minimum pressure. And this minimum pressure is important to know because if we have a liquid that's close to its boiling point or its bubble point, that liquid may flash into a vapor which will restrict the flow. Also, for flowing a gas through the control valve, the velocity at this minimum pressure may be so high that we approach the speed of sound, that is Mach 1, and that will also limit the flow rate going through the valve. When we look at control valve sizing, we have a number of heuristics which we must follow. For instance, if we know a design flow rate and we want to size a proper valve, the valve should be set either sized so that it's 1.3 times the normal flow rate, or if we know what the maximum flow rate that's going to be required through our system, it should be 1.1 times that maximum flow rate. When we look at pressure drop across the control valve, it's very important that we design it in such a way so that the valve pressure drop is equal to about 50 to 60% of the frictional losses through the piping system, or at least 10 pounds per square inch, whichever is larger. We should limit the maximum flow rate to minimum flow rate to a turn down of 5.1 if we use a linear trim valve, or 10.1 for an equal percentage trim valve. Linear and equal percentage will be described at another lesson in this class. And we should be able to control the flow so that the valve is between 10% and 80% of valve opening. Ideally, the valve should have a body size of one pipe diameter size smaller than the pipe in which it's installed. For instance, if we're installing a valve in a 4-inch pipe, we should select a valve body of 3 inches. Never ever select a valve that's larger in the pipe in which it's to be installed. Let's now look at how a valve performs with respect to the flow rate that goes through a valve. We're interested in the volumetric flow rate, V dot. And this might be gallons per minute or cubic meters per hour, depending on what we're interested in measuring our flow rate in. And that volumetric flow rate is going to be proportional to two factors. One is a valve coefficient, C sub V, and the second is the square root of the pressure drop across the valve. If we want a large flow rate, we would select a large CV or have a large pressure drop. If we want a small flow rate, we would want a valve with a smaller CV or smaller pressure drop. One thing that we have to be aware of with liquids and gases is areas where we have what could be called choking or cavitation. So let's take a look at what those mean. For a liquid, our flow enters in at P1 and then goes through the valve and we reach this minimum pressure. It's actually the pressure of the vena cava. And so the pressure drops down to this low point and then rises back up until we reach the pressure P2. Now, if we are above the vapor pressure of that liquid all the way through the valve, we have no problems. But let's take a look at what happens if we approach the vapor pressure of the valve. For instance, we could come in at P1 and then our pressure of the vena cava is below the vapor pressure of the liquid, and then it recovers back until we're above that vapor pressure of the liquid at P2. In this region here, since we're below the boiling point of the liquid, it actually flashes into a vapor, and then when the pressure rises back up, it collapses back into a liquid, and we call that cavitation. If our downstream pressure P2 is low enough, we will come in at P1, go through to where we're below the vapor pressure of that liquid and remain below. And this is what's called flashing because it just flashes into a vapor. Both of these situations will limit the flow rate of that liquid flowing through the valve. For gases, we have something that's very similar but has a different mechanism. As our pressure drop, in this case we'll use the square root of the pressure drop, as that increases, the flow rate going through the valve is linear with that, but then we start approaching the point where we reach the velocity of sound at those system conditions. And when we reach that point, then we can no longer get any more flow through since the speed of sound is the maximum flow rate we can get through that valve. And so we need to know exactly when this occurs. One of the things that we have to worry about with cavitation is when the liquid turns into a vapor and then rapidly collapses back into a liquid, we can cause damage to our material. Here we look at the effects of cavitation on a plug in a control valve, and you can see here that collapsing of the bubble actually will remove some of that metal and cause some damage to the valve. And so this can be quite a big problem if we're cavitating a valve. The second picture is a similar kind of thing, but this is actually a pump where we have cavitation occurring there. Both of these situations must be avoided, and so we need to make sure that we know if the conditions arise such that this could happen. So now we're going to first look at working with incompressible fluids, and that means liquids, and then we'll look at gases and vapors. Here we're going to look at the flow rate going through the valve as a function of pressure drop across the valve. If we have a situation where there's no pipe reducers, that means the valve body size is the same as our pipe size. We'll see that our fluid flows through the valve at increasing pressure drop. It's going to reach a point where we have flashing or cavitation occurs, and at that point the flow rate doesn't change with pressure drop across the valve. If we have some piping reducers in our system because our valve body is slightly smaller than our pipe size, we'll have a similar curve, although it doesn't go as high as the previous one. And again, we'll reach a point where we have cavitation and flashing occurring. And so we are interested in finding out when we reach this maximum pressure drop. And if that case is what's happening in our valve, we want to figure out ways to avoid that. so that we don't have cavitation and flashing occurring. So to do this, we first need some necessary information about our process. One of the key things that we're going to need is the specific gravity of the fluid at the temperature at which the fluid's flowing into our valve. We also need to know the vapor pressure at that temperature, which we call P star, and also the critical pressure of that liquid. And for the equations we're going to use, all these pressures must be converted to pounds per square inch absolute. We need to know the upstream and downstream pipe diameters, which are D1 and D2 respectively, and the valve lower orifice diameter D, and we'll convert all these diameters into inches. We need to know what the upstream pressure is and the downstream pressure. And these might need to be calculated based on the flow targets that we want. And then we're going to look at the valve coefficient of the valve C sub V, and this term called a liquid pressure recovery factor, F at L, at the desired valve position. In the United States, we typically have our C sub V in units of gallons per minute per inverse square root of the pressure drop PSI. So we're going to do a number of calculations to help us determine the flow rate through a valve. We're going to look at a liquid critical pressure factor, F sub F, and it's going to be a function of the vapor pressure of the liquid, which we call P star. And you might be able to have tabular values of P star, or you can use Antoine's equation to calculate P star. The critical pressure is tabulated in many data tables available to you. If you need a good source of critical pressures, you can look up the data in your Chemical Engineering Principles course. Knowing the valve diameter and the pipe diameter, we can calculate the inlet loss coefficient K1 using this equation here. We can also calculate the outlet coefficient K2. And we calculate a Bernoulli equation coefficient B1 and KB2 also. And then our overall loss coefficient is sum of K is given by this equation. Note that we have KB1 minus KB2. It's not added, but it's subtracted. So make sure you take care of that in your calculations. We then look at a piping geometry factor, F sub P, which is given to us by this equation below, which is a function of the valve coefficient, C sub V, the sum of the K's, and the orifice diameter D, and we can calculate it easily using the equation given there. We look at a combined pressure recovery and piping geometry factor, which we call FLP, and it's given by this equation below right there. And then we can calculate the maximum pressure drop to avoid cavitation, delta P max. And it's just the ratio of the FLP divided by the FP, square that, and multiply it by the upstream pressure P1 minus the piping factor F sub F times the vapor pressure P star. If the upstream and downstream pressure difference, that is P1 minus P2, is greater than the maximum delta P max, then we're given that the maximum flow rate V dot max by this equation given here. If the P1 minus P2 is less than delta P max, then we'll use the equation given below here where we can be sure that there's not any cavitation happening at all. Let's take a look at an example. In this case, I have water that's flowing through a 2.5-inch diameter pipe, and the temperature is 98 degrees Celsius, and the inlet pressure is 2 atmospheres. It goes into a 2-inch linear control valve that's 100% open, and the outlet of the valve goes into a 2.5-inch pipe where the liquid is discharged at 1 atmosphere of pressure. We want to determine what the flow rate of the liquid will be, noting that we could have cavitation. Notice that our temperature is at 98 degrees C, and if our outlet pressure is 1 atmosphere, we're very close to the boiling point of water, which we know is 100 degrees C at 1 atmosphere. And then we want to see what would happen to that liquid flow rate if the temperature coming in, instead of 98, is at 20 degrees Celsius. So at 98, we could have cavitation in the valve, and that will restrict the flow. But at 20 degrees C, we would expect not to have cavitation. We can look at some valve vendor information from a Mason-Nealing catalog, which we have available to us on the Course Blackboard website. And it gives data for various different styles of valves. In this particular case, I'm looking at a linear valve, and we have look at the data available, percent of plug travel. It gives us information going from 10% open all the way to 100%. We have data for S of L at these various different openings. And we also given another factor, X of T. We'll use this X of T variable when we're calculating whether or not gas flowing through the valve would reach sonic velocity, or the speed of sound. The valve body size are given in this table, and we're also given what the orifice diameter is in the valve, both upper and lower. And included in this table is the value of CV at different percent openings. So you can see at 10% opening, that valve has a coefficient of 4.8. And if we open the valve all the way to 100%, it's 48. We need to know what the density of the fluid is traveling at the system temperature. And so here I got some data off the internet, which tells me the density of liquid water as a function of temperature. And at 98 degrees C, we will find that our density in terms of grams per milliliter is equal to 0.96. Can look up our critical pressure in tables. In this case, for liquid water, it has a critical pressure of 218.3 atmospheres. Again, at 98 degrees C, the specific gravity is 0.96. And the vapor pressure at 98 degrees C is 13.68 psi. And we convert our upstream and downstream pressure of 2 atmospheres is 29.4 pounds per square inch absolute. And our downstream pressure is 14.7. Our valve coefficient is equal to 48 at 100% open, and the FL from that valve is 0.88. So here are the results using an Excel spreadsheet for the various calculations. And then I calculate my K1, K2, KB1, KB2. Also factor in my FLP, got my value of F sub F, and we can then look at my sum of my Ks, which is 0.263, using specific gravity and FL in this equation. I calculate my P1 minus P2 is 14.7. When I calculate my maximum pressure drop through the valve, we find that it's 12.08 psia, but my P1 minus P2 is 14.7, so I have choked flow. And the value of my volumetric flow rate at this condition is 166 gallons per minute. Doing the same calculation for 20 degrees C water, my maximum delta P is only 21.26 psi, and that's greater than my calculated delta P across the valve. So I would have normal flow going through that valve with no cavitation. And here my volumetric flow rate now is 183.2 gallons per minute. So in this case, I get more flow through that valve because I don't have any cavitation occurring. ChemCAD has ability to model control valves. In this case, we select a control valve and put an inlet and an outlet to it. And at the inlet, I have the 98 degrees C water going into the control valve at the pressure given at 29.4 psia. And I select a valve coefficient of 48. And I put in the critical flow factor of 0.88. I select a linear valve. And I check where I fix the valve position and adjust the flow rate on it. I tell it that the valve is 100% open. In this particular case, I'm telling it that my downstream pressure is 14.7 psia. And therefore, it will be able to model what's going on in this particular situation. And here I have a plot. I have flow through the valve in gallons per minute on my y-axis and differential pressure across the valve. That is P1 minus P2. And I have plotted on it for the data points I have for T equals 98 degrees C and T equals 20 degrees C. And at low differential pressure drops, my flow rate going through the valve is the same for both temperatures until I reach the point where cavitation starts to occur. And cavitation will occur at the higher temperature because we're close to the vapor pressure of water and it flattens out. Whereas with the 20 degrees C, where we're further away from the boiling point, that flow rate just continues to increase as I increase my differential pressure drop across the valve. I also have in the solid line the ChemCAD model, which is now kind of buried underneath the line I just drew. But we see the ChemCAD model for the 98 degrees C water will flatten out and give us the same flow rate as the values we calculated manually. And the ChemCAD model continues to increase at the 20 degrees C. But to get that to work out well, I had to do some manipulation of the critical flow factor C sub F that I use for the ChemCAD and the CV in order to fit the data. In this case, I used the same value of CV, 53.2, and my CF of 0.84, and I was able to predict the data quite well. And that's the reason why they're different is because ChemCAD uses a slightly different model than what we were using in our spreadsheet. So if we're going to use ChemCAD to predict a flow rate through a valve, we might have to manipulate the C sub V and the CF values to match those of what we're getting. Also, ChemCAD doesn't include the reducers in a pipeline and these geometry factors, so it's a little bit difficult for it to predict everything like we had calculated. Now let's take a look at the flow of compressible fluids, that is gases and vapors. Here we're going to have some information that we're going to need to know. One is the molecular weight of the gas that we have flowing through the valve, its compressibility factor Z, And you can calculate that using compressibility diagrams. If it's an ideal gas, meaning the pressure is moderately low and the temperature is room temperature above, we can say that Z equals 1. And we also need a specific heat ratio, which we call K, and that's just the ratio of the heat capacity at constant pressure divided by the heat capacity at constant volume. For true ideal gases, K will be 1.4, but other gases, that K will be different. We also need to know what the upstream temperature T1 is of the fluid that we have going into the valve, what the upstream and downstream pressure P1 and P2. We also need to know the pipe diameters upstream and downstream, and also the orifice diameter in the valve as well, and we want those in inches. We need the valve coefficient C sub V and the pressure drop ratio factor X sub T, which I had mentioned earlier at that desired valve position. We can now take a look at calculating our inlet and outlet loss coefficients K1, K2 using the parameters that we already looked at for the liquid phase calculations, and also our inlet and outlet Bernoulli coefficients KB1 and KB2, and calculate our overall loss coefficient sum K. Remember that we use a negative sign before KB2. Our piping geometry factor FP is given by the equation for it, which is just like our factor for the liquids. Here we're going to look now at our pressure drop ratio X, and that's given by the difference in pressure between the inlet and outlet and divide it by the inlet pressure. And we're going to now calculate a specific heat's ratio factor Fk, which is the ratio of K divided by 1.4. And since we're dealing with gases, we also have to calculate an expansion factor Y, which is going to be a function of our value of X, Fk, and X sub T, which we got from our valve coefficient data from the manufacturer's catalog. Now we want to check for choking. And the flow is choked if a value of X is greater than that product of F sub K times X sub T, or if the value of Y is equal to 2/3. Either one of those cases would tell us that the flow is choked. If our valve doesn't have any reducers, meaning its valve body is the same diameter as the pipe that feed it, then this coefficient XTP is just equal to X sub T. If we do have reducers, then we would calculate XTP using this equation, which is a function of XT, the FP, K1, and B1, X sub T, and the ratio of the valve coefficient divided by D squared, and that quantity is squared. So we would calculate XTP in this fashion. If we have choking, then the maximum volumetric flow rate, and notice that now my units are in cubic meters per hour, is given by this equation where it has a coefficient 1495, our value of Fp, the upstream pressure P1, C sub V for the valve, molecular weight of the gas, upstream value T1, compressibility factor Z, and Fk times XTP. Here, note that my P1 must be in bar, absolute pressure, and my T1 in this case must be in Kelvin. If no choking exists, our volumetric flow rate can be calculated using this equation. Again, our pressure will be in bar, a temperature T1 and degrees K. And Again, our volumetric flow rate will be in meters cubed per hour, but that flow rate is calculated where we have a reference condition of 1 atmosphere and 15.6 degrees Celsius temperature. So the coefficient 2250 takes takes into account the upstream pressure, and we calculate it at 1 atmosphere. And these are the same conditions for the choked velocity, is also at 1 atmosphere and 15 degrees C. Let's take a look at an example where I have hydrogen instead of water flowing through the same pipe. The inlet pipe diameter is 2.5-inch diameter. Temperature of the hydrogen gas is 25 degrees C, and the inlet pressure is 50 pounds per square inch absolute. We go through a 2-inch linear control valve that's 100% open, and the outlet of the valve goes into a 2.5-inch pipe where the gas is discharged. I want to look at the molar flow rate of hydrogen as a function of the outlet pressure. That is, I'm going to vary P2 at different values and look at what the molar flow rate is actually happening for this hydrogen stream. And I can do this by using the equations that we seen before. We notice that this flow rate given by the data symbols, where I have molar flow rate and kilomoles per hour as a function of delta P across the valve. And here we find that the molar flow rate increases as a function of delta P until I reach the point where I get choking. And here the valve now has such a large delta P, we reach sonic velocity, and that flow rate doesn't change. I did the same simulation using ChemCAD. I had to modify the CV to be 46 and the critical flow factor to be 0.98 in order to use the ChemCAD model to fit the data as best I could. And so when we're dealing with gases, we might have to do some adjustments in ChemCAD for the valve coefficient in the C sub F in order for it to give us the results that we calculated with the rigorous equations.